Alrighty, so this is the lecture video for day 8. Hopefully you're watching this before Wednesday. Today we're talking more about linear regression. So we've been talking about this really powerful tool that lets us take a data set, so take some scatter plots, and fit a line to it. And by doing so, the line itself is going to tell us things about the relationship between the variables in our data set. And I've mentioned a few warnings, a few cautions as to how we can actually interpret this data set, and I'm going to do that a little bit more today. And then we'll get into a way around a couple of those issues. Anyway, so the main issue that I'm alluding to is that we only can use linear models when the relationship is linear. As we've seen a few times, we can have associations that are not linear, and they can still spit out, let's say, very high R values, very high correlation coefficient values. And that doesn't necessarily mean that it's a linear relationship or not. In order to determine if it's a linear relationship, we usually have to just look at it. So we're going to be doing that a little bit more today, and then talking about what we can do if it's not linear. Is there any way that we can actually get some meaning from this data? Well, yes, we're going to rescale it, re-express it in some way. Okay, so the first warning that I have for you today is to avoid extrapolating a linear model past the endpoints of the values that we have. So let's take a look at this example. So we have the average age of various people's first marriage. And so I've blocked off some of the data because I want to pretend that we are studying this in 1940 and we are looking at the trend over the past 50 years. So if we have these collection of data points, so this is for men would be these data points, women would be these data points. Let's say in 1900, the average age of first marriage for men would be about 26, and for women would be around 22. And we can see, looking at this graph, that, well, I'm not actually going to plot it, but if we were to calculate the linear model, if we were to find the least squares regression line for, let's say, the men and the women separately, we might see that it has, well, generally a downward trend. And we might look at this and be tempted to say, oh, well, in the next decade, they'll be even lower. And maybe by the year 2000, people will be getting married, on average getting married in their teenage years or something along those lines. So just by looking at this data set, both of these fits, I think, are actually pretty good. These both look like linear models, and they probably have very good R values. But the word of warning is that what this tells us is that in this range, in the range for the X values of points that we have, the model might be pretty accurate. But it says absolutely nothing once you extend beyond these endpoints. So we just have to be very aware of that and avoid trying to extrapolate to points out here. So I say that for a lot of data sets, like, part of why you're doing them is to try to say something about the future. Everyone wants to know what's the trend, where are things headed. So if you absolutely must extend a model beyond its maximum data point, then make sure that you are doing so responsibly. And what I mean by that is, don't extend it too far. Point out that our model doesn't necessarily say anything beyond this, and we are extrapolating as to where the values are. And acknowledge that as time goes on, the value of our prediction is going to get worse and worse. So those of you who end up using linear models at some point in the future, may be tempted to go down this road of trying to predict the future, just be careful with what exactly you say. Try to use words that say that, oh, the past trend may indicate something in the future, rather than saying, oh, our linear model says that by the year 3000 people will be getting married before they're born, which obviously isn't true. Okay, so now that I've been pointing at this enough, I want to remove that just to point out how drastically wrong an extrapolation beyond these points would be. All right, so as we can see, the average age of first marriage starts to go up fairly rapidly, starting around in the 50s. The second word of warning I have for you is one I've said a couple times by now, and that is correlation does not imply causation. I had you all look at a few spurious correlations, which very obviously are not indicating any sort of causality statement. So just because you can make a scatter plot with a very good fitting line, a very high R squared, a very high R value, doesn't mean that there is necessarily any causal statements. So be very careful with how you phrase any interpretation from these models. And then the third word of warning I have is that just because we have the mechanics to make a linear model doesn't mean that we should. So fairly often we'll have some distribution where we can get a line to fit it and maybe even have a really good correlation coefficient, but maybe the line isn't the best tool for the job. So next we're going to be talking about one way to identify if a linear model is actually appropriate, and then what to do if it isn't. So just because an association isn't a linear relationship doesn't mean that we might not be interested in it. So we want to talk about the things that we can do to rearrange or re-express our data so that we can take advantage of these linear models. Okay, let's take a look at an example of this using R. So in this R Markdown file, I have my title information, I have my setup, and then I added this dataset generating code chunk. Feel free to take a look at it, but we're just going to ignore this for now. We're going to hit run, that's going to generate our datasets, and then we're going to move on from there. So I have X and Y values. Let's say that the X corresponds to time and that the Y values correspond to population. Could be the population of some bacteria in a petri dish, maybe population of animals on an island, what have you. The point is, I want to compare these two quantitative variables. Great way to do that is a scatter plot, and let's see what we get. Cool. So here is my data set, and what I want to know is there some way to model this? Is there some way to extract some sort of meaning, some sort of statement about whatever happens to be going on here? So the way that we've been talking about doing something like this would be trying to fit a linear model. This data set I would characterize as pretty strong, positive, but not necessarily linear. It looks fairly straight, but as it turns out, we're going to end up checking the residual plots, and it's going to sort of further emphasize that, hey, maybe a straight line isn't quite what's happening here. All right. So we're going to walk through how we are going to make those plots, how we're going to determine that this isn't necessarily a linear association, and then what to do next, how to address it. Okay, so let's go ahead and make a linear plot just to see what that looks like. So there's a few ways of doing it, but I think the easiest is to define a model. So I'm going to say my REG is abbreviation for regression, that this is what I am calling the linear model, so LM y tilde x. It always sort of seems backwards to me that you use plot of y of x, y tilde x, and lm of y tilde x. And the reason it is the way it is because what we're plotting is y, and then x is how we're breaking that up. Anyway, we want to use the linear model of our response variable than our explanatory variable. So we can just run this by itself, but because we're going to reference this in the future, I'm going to give it a name, reg. So now one thing that we could do is that we could add in the line generated by this linear model. So if I add in abline is a command that adds a line to whatever plot you most recently ran. So because I just ran the plot that made this first picture, if I run abline reg for regression, this should add the least squares regression line to the picture. Okay, good, that worked. So with this line, it may help emphasize that the relationship here isn't quite linear. Points on the low end seem above the line, on the high end seem above the line, but in the middle seem below it. One even further way of illustrating that would be to make the regression plot. So I'm going to make a new plot, and rather than comparing the y values to the x values, I'm going to compare the residuals of the regression model compared to the x values. And then if I spell residuals correctly and we run it, we get a picture like this. So this is the residuals plot, and I think this very much illustrates the fact that our original plot wasn't quite straight. So this is saying we can't use a linear model. Or rather, it's saying we can't use a linear model with the data as it is. But we would really like to be able to talk about this relationship. We want to be able to get some sort of meaning out of this data set. And just because the relationship isn't linear doesn't mean that we should just give up on it. So at this point, you could sort of go one of two ways. We could start saying, oh, well, let's do a nonlinear model, maybe an exponential model, and plug in a bunch of extra variables or extra parameters that's going to allow us to tweak that model. And that is a way to go, but as it turns out, sort of the much simpler thing to do is rather than allow our model to change, we're going to re-express our variables, we're going to rescale our variables so that it does fit a linear model. In other words, we're going to be taking the y values or the x values, or both, and either expanding them or contracting them in an effort to make this relationship be more linear. So in this particular picture, what we would like to do is contract the y values. If we were to, let's say, go through and square all the y values, that's just going to exacerbate the problem. The bigger points are going to get bigger, the smaller points aren't going to change much. Instead, we want to do something that contracts it. And so we might say, all right, well, what function should I use to contract it? And this is where the law of powers comes in. So powers that are greater than 1, so 2, 3, etc., if we were to cube the values, that's going to expand everything. However, values that are less than 1, so if we were to take a square root, that's like a half. If we were to take a log, which is sort of like a 0, or if we were to do 1 over the value, which is essentially -1, these are all transformations that are going to contract that axis. Okay, so our goal is to contract the y values. Because we're working with populations, a good place to start is logarithms. If we're working with counts, typically instead you start with square roots. And you can start with one and then switch to the other, that's fine, but these are just good ideas of a power to try right off the bat. Okay, so what we want to do is we want to reformat our data set so that rather than the y values being between 0 and 1500, we want to take each individual value and take the logarithm of it. And if you're not totally comfortable with logarithms, that's okay, because R will do it for us. So let's go ahead and play around with logarithms in R. And by that, I just mean, let's say, what is log of 22? Or let's choose one of these points. One of these points is about 500. What I want to do is I want to reformat each of these 20 points. So for this particular point, I want to change it from y equals 500 to the log of 500. You might be interested in what the log of 500 is. R will just tell us. Hey, it's 6.21. Great. The reason I'm bringing that up is because not only will the function log of a number calculate the log of that number, we can ask R to apply this to an entire list. So our y values, where is it? Way up top. I minimized it. Our y values are going to end up being just a list of 20 numbers. So here, let's go ahead and just write down what y is. Y is these 20 numbers. If I were to take log of y, so log of a list of numbers, it applies log to each of those elements. So if I were to run this, we get our first list, which is just y, and then our second list, which is the log of y. And this applies to just about any numerical calculation. If you run a function that typically is something that you would do to just one number, if instead of a single number, it's got a list of numbers, it's going to apply that function to the whole thing. So if instead of y, we wanted y plus 2, it's going to add 2 to each of the values. So 1563, 1565. Great. So what we're going to do is first get rid of this. We aren't actually concerned with what those logs are. Is that we are going to define some new variable, so I'm calling it new y, to be the log of y. And then we're going to run through this exact same procedure. So we're going to do that in a second. But let's see what this looks like. So I have here, I'm plotting the new y versus x, and I changed the y label to, instead of be population, to be log of population. And then here's my new picture, which I think looks pretty good. This is also a very strong association. It's now, I would say, linear, and it's still positive. So we don't want to, as always, we don't want to just assume that it is in fact a linear relationship. So we want to check it. And to do that, we want to do the exact same thing that we've been doing. We want to define the regression model. We want to make the residual plot, and we want to see if we can see some sort of pattern. So running this, we can see our linear model pick up this this least squares regression line, and that looks pretty good. And then I can look at the residual plot, and we can see that while it might be the case that early on they're a little bit more spread out and later on they're a little bit more compact, there's no trend where points that are early on are above the line or in the middle are below or anything along those lines. There's no obvious curving. At any given point, we don't really have a hunch as to if the residual is going to be positive or negative. it's roughly evenly scattered above and below the line. Which, these are all indications that our model is actually a pretty good linear model. Okay, so we will leave it there.